Okay, this is Cal 2, and 4 minutes late getting started. I only got one person in the staff class beside me, so hopefully others will be coming in. That didn't work. No. The only announcements I know about is a job opportunity. This was sent by Coach Jonathan Jefferson. I don't know him. I don't know what he coaches, but he said he's a coach at Boston State. It's about a company named No Kid Hungry. The job title is Brand Ambassador. It has a job description, a company description, and a place for you to contact him by email. Not him, but the person, Henry, whoever Henry is, and has an email address. And weekly wages, $350 a week. So that's all I know about it. If you're interested or know of anyone who's interested, feel free to get the information off of here. Ryan's here. So the top part of the alphabet is doing pretty well. The rest of them are not anywhere to be seen yet. Okay. The next one I think I've announced to you before, so I won't go over it in great detail, but it's the Summer Research Experience for Undergraduate by UAB. The topic of this one is Experimental and Computational Materials Research. And I don't think I've got that on the board here. I'm not sure I don't. That was last year's. I hope they didn't send the wrong one. I may take that down. Yeah, I thought they sent a new flyer, poster like that, but that's last year's. Let me see if the dates on it are correct. Yeah, this is last year's. This isn't this year's. It's supposed to be one same type deal. But it's not. Okay. It's that program there is just for this year rather than last year. So you're welcome to look at that. I imagine a lot of the information is the same. But if you want more information, I have it here. It looks like a great opportunity, and I would say take advantage of it if you're interested. You got the information here. I'll be glad to share it with you. All right, that's that. Now, I don't remember if I said this on Monday or not. No, I don't believe I knew it on Monday. Sometime Monday, they finally opened, as far as I know, student course evaluations. Have y'all seen that yet? Yes. Okay. It happened Monday, so I probably didn't announce it in class. I've been asking for weeks when are they going to open them. They finally got them open. So please do the student course evaluations, okay? If you don't know or remember exactly how to access it, the easiest way, go to your email. Find the email they sent Monday, and when you open that, you'll find the link. Click on the link, you're there. And it's easy to do. Otherwise, one person said they thought you could open it through Blackboard. I've seen a place there in Blackboard, but I've never done it through Blackboard, so I can't specifically tell you how, but there is a place that said course evaluations or something like that. But I know you can access it through the website. But again, that's a little more involved. The easiest way is to go through your email and click on that. Okay. Now, still I've received one, and only one, research paper. So please, folks, they're due today. Okay, and if you're going to send it to me, if I receive it today, you'll get full credit. If I receive it tomorrow or later, you'll start losing points. So please get those in. The first test I was going to return to you today, but the people here have not turned them in yet. Is that what you got here? That's this research paper.
Test one.
All right. Test one? Yeah. Okay. So please get those to me as soon as you can. Test two. I've received 2 test 2s. So please get me test 2. Preferably today, but as soon as you can. And before you leave today, I will be giving you test 3, which is the last test. You can call it the final exam if you want to. It is the last test. So in that sense, it is the final. It's not comprehensive, but it is the last test you'll have. Okay? And I'll give it to you at the end of class. Okay. Let's see, what else? Okay. When do you turn it back in? Well, let me give you my schedule for the rest of the term. I'm here on this campus all day today up until 4 o'clock. 4 o'clock I leave to go to the Birmingham East Campus, where I have a physics class, last physics class of the term there, and I'll be there until 6:30. What's that?
You taught physics, sir? I did not know you taught physics.
Yeah, I do. Most of the time Dr. Bryant teaches it, but I do teach it sometimes. Most of the time when I do teach the regular physics, it's in the summertime when we have the transient students in. The last couple summers we haven't had enough to make 2 sections of any one, so he's wound up teaching even in the summer. But this is the physics for the diagnostic medical sonography program, so I'm teaching that one. Okay. The reason is he can't teach for so many hours because he's an adjunct. So I'll be over there until 6:30 this evening. I'll leave here around 4. Tomorrow, I'm on this campus from 8 in the morning until 8 in the evening. Okay? I do have classes tomorrow. I have a class from 8:30 until 9:45. Another one, my regular classes on Tuesday and Thursday. Okay. Then Friday, here's a change. Normally I'm on the Birmingham West Campus on Fridays from 8 to 12. Tomorrow I'll only be there from 8 until 8:40 approximately. I have a doctor's appointment at 9:20, so I'm going to have to leave that campus by 8:40 in order to make the doctor's appointment by 9:20. So if the doctor's appointment gets over with in time, then I will be going back to the Birmingham West Campus. But it's my annual physical, and the doctor canceled on me last spring when it was supposed to be, so it was rescheduled for, and they said when they told me you were canceling, I said, well, when do you want to reschedule? Well, the next available date is, they said, October or November. I said, well, I need it on a Friday. Oh, well, that'll be December. So that's why my thing is there. So I don't know how many tests and blood work or anything else he's going to have. That could all lengthen it out. If there's nothing extra he wants to do, I'll probably be back on the Birmingham campus, but I just don't know what time. But I won't be back there if I leave UAB anytime after 11:30. I won't get to West Campus and then turn around and go home. That doesn't make any sense. So I'll get there if I can, but I know I'll be there 8 to 8:40. Okay. Now, next week, let me go over how things will be. I'll give you your last test today, and that's due next week, anytime next week. Okay? Here are where I'll be, what I'll be doing anytime. Monday of next week, I'll be on this campus in my office, 265, pretty much from 8 in the morning till 6 in the evening. All my classes are doing take-home finals, and they'll be turning them in to me there. I won't be up here in the classroom teaching a class or anything. It's finals week. Okay. Tuesday, I have a final from 8 until around 10, and that's going to be down the hall in room 205. Okay? So Tuesday 8 to 10, I'll be in 205, around 10. Okay? I may be a little longer than that if some of them aren't ready yet. You know, aren't finished in time. Okay? So that will be the morning. Then from 10 o'clock until 3:15, I will be in my office, 265. 3:15, we have my last physical science class. We're going to be doing a lab and a test. And that's all we're going to be doing in that. It'll probably be through, I'm guessing, 2 to 3 hours. Normally it's 4.5 hours. It's not going to take that long for them to do the lab and the test. So I'm going to guess 2 to 3 hours. Maybe 2.5 to 3 hours. Okay. Then after that, I'll be back in my office until 8 o'clock in the evening. Okay, that's Tuesday. Wednesday, in my office all day from 8 in the morning until 4 in the afternoon. Because Wednesday at 4, I'll have to go to the Birmingham East Campus to collect the finals from that class. So I'll be there from 4:30 till 6:30. Okay? Thursday of next week, 1 week from tomorrow, I will be in my office from 8 until somewhere close to 3 o'clock, okay? Because I have a final exam in this room at 3 o'clock. Now, the final will not take very long, so I probably won't be up here very long at all. But I'll be up here until all of them finish the final, and I'll be back in my office. That's Thursday. Then Friday of next week, I'll be on the Birmingham West Campus as normal from 8 to 12. No doctor's appointment or anything else. But after 12, I'll still be there because graduation is at 1 o'clock. So I'm going to stay for graduation. And so I'll probably be in my office past 12. I don't know what time they want us to show up for graduation. Sometimes they want us at about an hour early. Other times, they're not that picky about it. Yeah.
Hey, I'm kind of sick today,
Yeah.
so if I could just get the test.
Okay. Yeah, I knew you were barking yesterday. So.
I'm headed to the doctor.
Are you? Okay. That's wrong class. 3. I apologize ahead of time. It's way too short and way too easy. But what I'd like you to do, I'm going to give it to you. You have something to write with?
No.
Okay. All right, with this. I didn't realize until after the copy was made, I left off the function on the last problem. It's a parametric equation, set of parametric equations. That's what it is. You can copy it on yours. And then I was going to put it on the board, but you won't be here to see it on the board. Well, if you listen to YouTube video, you see it there because I'll put it on YouTube video. That will be protected on the board. Okay. Thanks. Hope you feel better. And let's see. I'll give you your other stuff when you turn in your final. Okay. Okay. Sorry about that. When he wasn't here first thing, I figured, because I could tell he didn't feel well yesterday. He was coughing almost as much as I was. Okay. So, I got up to Friday of next week, and I'll be on the Birmingham campus from 8 to 12, and maybe past that until whatever time they want us to go to the gym, I think is where the graduation will be. So whenever they say we have to be there, I'll leave my office and go over there. After graduation, I'll probably just go back to the office, pick up my stuff, and go home. So now, that gets you through next week, finals. Everything's supposed to be in sometime next week. Now, are any of you graduating? I don't think you are you? Okay. Then the following week, grades are due in, I think it's noon on Monday. So I will definitely be here from 8, probably until 6 on Monday. Okay, once I get grades. What's that?
So that's next Monday?
The Monday.
Okay.
The Monday after next week.
This is the Monday after next week. Next week is finals week. Yeah, I'll be here on this campus. So if you don't get everything to me next week, you can try to get it to me that Monday morning if I have time to grade it and get all the grades calculated and stuff like this before noon. I'll get it in. If not, you'll get an incomplete until I get time to get it done, and then I'll do that. I'll also be here on Tuesday. They require us to be here Tuesday and Wednesday. However, I can't promise they're not going to have us in meetings. They sometimes do that to make sure we show up. Micromanaging, is that hyphenated or not? I don't know. Never mind. So I don't know where I'll be Tuesday and Wednesday. I'll be on this campus Monday because that's where grades are due. But then Tuesday and Wednesday, they may have us over on the Birmingham campus. They may have us here. If they leave us alone, I'll be here. And I'll be working. Tuesday, I'll probably be here 8 till 8. And Wednesday, probably 8 till 6, maybe even 6:30. I'm going to try to get everything done for next term before I leave. After that, I won't be back till January. Okay. So if you don't get everything into me, you can get it to me that following week. I'll give you an incomplete and then change the incomplete before even the term begins. Yeah.
Okay, so Monday, I'm just kind of recapping, make sure I got it right. So Monday you'll be here all day. Right?
Yes.
This coming Monday. Tuesday you'll be in Bessemer?
I'll be here in Bessemer all day, but I've got a final at 8 to 10, and I've got a class 3:15 until, I'm guessing, around 5:15, 5:30, something like that.
And then Wednesday?
Wednesday here all day from 8 to 4, and then I'm over on the Birmingham East Campus 4:30 to 6:30. Half hour in between, I'm driving over there. And on Thursday, I'm back here all day, 8 to 8, but I have a final at 3 o'clock. It won't take long. So except for that final in this room, I'll be in my office. And then Friday, Birmingham West Campus, in my office over there, Dr. Pruitt's suite of offices. I'll be there 8 to 12, 8 until whatever time they tell us we have to be at the gym for graduation. If they tell us we have to be there an hour early, I'll be there at 12. If half hour, I'll be there till 12:30.
You said you're going to be in Dr. Pruitt's office?
Yeah, that's where my office is.
Is that like where Miss Saxton's?
The what?
Is that like where Miss Saxton's office is?
Yes, yes.
Okay.
You know where her desk is. Right behind her desk is the copy room. That's where my office is on Fridays. And Dr. Pruitt's office is the big corner office. Yeah, that's where I am on Fridays. All right. Any questions? Okay. And as I said before, some of you got in here. I have only received one research paper so far. They're due today. I've only received 5 of the 9 of you have turned in the first test. One more came in today. So that's 6 out of 9. So 3 are still missing yet. And test 2, only 2 people have turned that in. So 7 of you are missing test 2. And then I'll be giving you test 3, which is the last test, the final test, today, before you leave. All right, any questions? And I went through all the schedule. Oh, and for those who came in later, they have finally opened student course evaluations. I've been asking about those for weeks now, and I found out yesterday they opened them on Monday, okay, but it was after, I didn't know about it when we had class Monday. Okay, so please do those. What's that?
I don't know, I feel like if they opened it like at 3 or something.
3 in the afternoon or morning?
In the afternoon.
Afternoon, yeah, so it was even before this class began. See, I don't see, if they do the email to faculty and student at the same time, then I'll know when it is. But if they do them separately, they probably did them at the same time, but I don't know. I just heard about it yesterday. Okay. Any questions then? Please do the student course evaluation. Please get me your research paper. Please get me your test 1 and 2, and I'll be giving you test 3 today. All right. Now, where we left off last time was example 1. Okay? And that's what's up here now. This is in chapter 10, conics, parametric equations, and polar coordinates. Okay? And that's chapter 1, yeah, it's kind of 10.2, chapter 10. 10.2 is plane curves and parametric equations. And here's Dawson. Again, the top part of the alphabet doing quite well. Poor old Patrick was the only one holding up the bottom half, and he left. So, any questions? They finally opened to the course evaluations. Please do those. Easiest way to access them, go to your email, open it, there's a link, you're there. Otherwise, you have to go to the website. Somebody said they thought you could do it through Blackboard. I've never done that, but if you can, that's fine too. The easiest way is through your email. Okay. And research papers are due today. First test were due a while back, but I'll take them today. Second test, due a while back, but I'll take them today. You're getting the third test, the last test at the end of the class today. Okay. Any questions? And if you want to hear where I will be this week and next week, listen to the YouTube video because I went over it in gory detail. Okay. So here's example 1, near the top of page 701. Sketching a curve. Okay. Says sketch the curve described by these parametric equations. Oh, here they are. X is equal to f of t, which is t squared minus 4. Y is equal to g of t, which is t over 2. I was going to say 1/2. That's not very interesting. Where t is between -2 and 3. Now, you can do this however you want. Here's the way I found I like doing it. Okay? You can do it any way you want. I know they used to call them t-tables. This is a t-table with 3 columns, okay? The book does it horizontally. I sort of do it vertically. I like horizontal most things, but, we'll do it this vertically. I always let me get my pen set up, okay? I always put t first, then x, and x, of course, is t squared minus 4, and then y, which is t over 2, okay? And they give you the values, and why not use integers? That's fine with me. We'll start with -2, -1, 0, 1, 2, and 3. Okay? That'll give us enough points to get started. Okay? Now, there's your t. You tell me what x is. So x is t squared minus 4. When t is equal to -2, what's x? Say again? 0. Okay? What's your y? Say again? I'm sorry, -1. Okay? When t is equal to -1, what's your x? -3. What's your y? -1/2. Very good. When t is equal to 0, what's your x? -4. What's your y? 0. Okay. When t is equal to 1, what's your x? -3. What's your y? 1/2. Positive 1/2 this time. When t is equal to 2, what's your x? 0. What's your y? 1. And when t is equal to 3, what's your x? 5. And what's your y? 3/2. Okay, very good. So let's now...
So, what's y equals what exactly? Is that t over 2 or is that...
Okay, say that one more time. The y is t over 2.
Okay.
Yeah. I got confused by it too. It looked like 1/2 on the first glance, but that can't be true. And now I realize that's a t. T over 2. Over there too. Okay, so let's set up our axes. Okay, and we'll go. Now you set up axes for X and Y. T doesn't show up on here at all. The influence of T shows up, but not anything else. Your X is going from -4, 1, 2, 3, 4, to +5. 1, 2, 3, 4, 5. Your Y's are going not very far. From -1, I'm going to do them by halves. -1/2, -1, -3/2. +1/2, +1, +3/2. That's all you need, okay? So these are by -1/2, -1, -3/2, 1/2, 1, and 3/2. Okay. This is -1, -2, -3, -4. We could put a -5 if you put a -5 and call it 7. I don't know what I'm writing, okay? Okay. And 1, 2, 3, 4, 5. And you could put one more if you wanted to, just to get 6. All right. Tiara's here. If I could quit coughing. Reminds me of a dumb joke. No, I won't go into that. Okay. So sorry about interrupting again. Let me say this for everybody who comes in, so you'll hear it many times if they keep coming. Finally, they've opened student course evaluations. They just did it Monday afternoon after this class was over with. I found out about it yesterday. I forgot to tell my first class, but I told the later classes, please do the student course evaluations. They're very useful to us. I'm a department chair. I use them big time when I'm doing my evaluations. I'm required to evaluate all my instructors once a year. That's the main thing I use. So please do the student course evaluations. Okay? They also will probably ask for a few other potential things for you to evaluate, like the registration procedure, library, food service, housekeeping, grounds, whatever, maintenance, that kind of stuff. Answer those as well, because we get feedback every day that we see you, whether you know it or not. You know, if we don't interact in class, I at least can read your body language and eyelids, or whatever, you know, and so I know some feedback. Those folks, they don't get it every day like we do, or every time we meet. So please do your student course evaluations. Research papers are due today. First test have been due for a while. Second test have been due for a while. I'll be giving you the last test today. And I'll be here all next week, so you can turn things in. I'll be here all day tomorrow. If you finish early and want to turn them in then, I'll be here all day tomorrow. And then Friday I'll be on the Birmingham West Campus, but not for very long. This coming Friday I have a doctor's appointment at 9:20, so I'll only be there from 8 to 8:40. Then I'll leave and go to my doctor's appointment. It's my annual physical. I don't know how long it's going to take, how many tests they want, or anything else. If there's a lot, I may not be back. If there's not that much, I could be back. I figure it's going to take at least an hour, so that'll be till 10:20. And so the earliest I'd be back to the Birmingham campus would be 11 o'clock, I think. But if they have me do lab work or something like that, those things are usually very slow, and I may not make it back at all. So you can only guarantee I'll be there 8 to 8:40. Okay? I hope to get back after that, but we'll see. Okay, and then you can turn in the test anytime next week and listen to the YouTube video. The first part of this, I went over in gory detail, all that stuff. All right, so let's plot our points here. We're plotting XY. We're not plotting T. T is what we calculate our XY by. So when x is equal to 0, y is equal to minus 1. There's a point. When x equals negative 3, y is equal to negative 1/2. There's a point. When x is equal to negative 4, y is equal to 0. There's a point. When x is equal to negative 3 again, y is equal to positive 1/2. So this definitely is not a function of x. Okay? Looks like it could be a function of y. The reason is they're both functions of t. These are not independent variables, x and y. They are dependent on t. Okay? When x is equal to 0 again, y is equal to 1. And when x is equal to 5, y is equal to 3/2. Right about there. Okay? So here's the function in this interval for t. It starts here. I'm going to draw it backwards because I'm left-handed and it's hard for me to draw that way. It goes like this. It looks like yuck. It stops right there. We don't go this part here. Okay? So forget about that. Okay? Stops right there. It goes from here. Now, because it's a parametric equation, it has an orientation, a direction, and it's going in that direction. Because the least value for t starts down here, the greater values for t are up here. So you need to put an indicator, an arrow, indicating which is the orientation of the parametric equation. Now, sure enough, that is part of a sweeping parabola, isn't it? Okay? That x is a function of y, not y is a function of x. Okay. Okay. That's how you sketch the curve. Any questions about that? Okay. They say some of the same things I said, so let's see how they do it. Okay, this is on page 701. Let me clear my stuff. Unless you have any questions, can I clear it? Sound like ER. Clear? Okay. Okay. They do a horizontal tape or whatever you want to call it. Okay? They put the T's in the top, and they pick the ones just like we did, and then they calculate the x and the y based on the parametric equations. And then they plot the x and y. So there's their table, just like we had. Here's the plot. And they also put 3 arrows. You don't have to put that many, but you can put as many as you want, just to indicate what the orientation is. Begins here, ends there, because that was the domain for t. T is the independent variable. Both x and y are dependent on t. So t is the independent variable here, and it's going from -2 to 3, and it stops. Doesn't go anywhere beyond those. Okay. Any questions? Now, if you had t going from negative infinity to positive infinity, you would have had the entire parabola. Okay? But we didn't. We just had those values, so that's what we got. Okay. Any questions? Now, the next thing they're telling us how to eliminate the parameter. Why don't we do that for this one? They're going to take you to a different one, but here's how you eliminate the parabola. Okay? Okay, eliminate the parameter, not parabola, parameter. Pick the easiest one to do. Your parameter is t. The y here is the dead giveaway. Solve for t. Multiply both sides of this by 2, and you get these, the 2's go out, t is equal to 2y. Right? Pretty easy, right? Now, plug that t into the x, and you get 2y squared minus 4, which would be 4y squared minus 4. Okay? And if you wanted to, you could take that down and say 4 times y squared minus 1. Okay. No real reason to do that, but you could. So that shows that x is a function of y rather than y being a function of x. There's the function, and that gives you the entire parabola. There's nothing here that says you're limited between t equals -2 and 3 because you did away with the t. So that would give you the entire parabola, but it's that sleeping parabola that went like that. So it's a, actually this form is probably the better one to use because you see it has a horizontal displacement 4 to the left, okay? And it has a, you would say a vertical stretch, but it's a, see, we're used to having them oriented like this. When they're oriented like that, that would have been a vertical decrease and a vertical stretch. Now it's a horizontal displacement to the left 4 and a vertical stretch by 4 times. So that's why the parabola was long and skinny, but moved over 4 places to the left. As we saw here, you see, it's skinny because of the horizontal stretch and a horizontal displacement 4 to the left. That's what we had. But now when you eliminate the parameter, you get the whole parabola. So let's see how they tell us. Finding a rectangular equation that represents the graph of a set of parametric equations is called eliminating the parameter. Let me give you a hint. You can't always do it, okay? Or sometimes it's incredibly complicated, and you don't want to do it, okay? But that was a simple one, and you usually do this when they're fairly simple. For instance, you can eliminate the parabola from a set of parametric equations. Oh, it's using that one. I'm sorry, I thought it was using a different one. The easy one to do here is the y. So solve for t is equal to 2y. Plug that into the x, 2y squared minus 4, 4y squared minus 4. So they did do it, sorry. I was looking at example 2 and thinking that's where they were going to do it. So that's exactly what we did. And once you have eliminated the parameter, you recognize the equation represents a parabola, horizontal axis and vertex at -4, 0, as shown here. Now, once you eliminate the parameter, though, there's no guarantee. You have no way of knowing where the p's are anymore because you don't have them in there anymore. So that equation that we got, that one right there, looks like it's the entire parabola. You don't necessarily know it starts here and stops there. You just have to do that with the parametric equations. All right. The range of x and y implied by the parametric equations may be altered by the change to rectangular form. That's what I was just saying. In such instances, the domain of the rectangular equation must be adjusted so that the graph matches the graph of the parametric equation. And that's what you have to go back and scratch your head and figure out. So why not leave it in the parametric form? Why change it to that if you're concerned with that? Okay. Here's example 2, a little bit more complicated. Sketch the curve represented by these equations. X is equal to 1 over the square root of t plus 1, and y is equal to t over t plus 1. Okay. Now, before you even begin, any bells go off when you see this? Warning signs? Okay, you've got a square root in the denominator. It's okay to have it there. I mean, a lot of mathematicians don't like it, but it's okay. Okay, but what's more important? What about square roots?
You can't have anything less than 0.
Okay, you don't want the denominator being 0. Either this one or that one. What would make either one of those the denominator 0? T is equal to -1. So obviously T cannot be -1. That's all you get from this one, but you get something else from this one. What's that?
Can be equal or less than
Okay? Actually, T has to be greater than or equal to -1 to satisfy this, because the denominator has to be greater than or equal to 0. Subtract 1, you get T greater than or equal to -1. But it can't be -1 because it's in the denominator, so that would make it 0. So it has to be T is greater than -1. So that's all we've got here. So that is saying that we're going to use all available T's. We're not starting and stopping any place like we did before. You can't do any T less than -1. It can't even be -1. All right. So it says sketch the curve represented by those equations by eliminating the parameter. Oh, boo hiss. Okay? And adjusting the domain of the resulting rectangular equation. I promise you it would be far easier to just do it parameter-wise. But they say by eliminating the parameter. So you tell me which you think would be the easy one to use to eliminate the parameter. There's pros and cons for both of them. You can use either one. Which one would you say? Parametric equation for X or the one for Y? I like Y too. So what would we do? First step. What's messy about Y? It's also messy about X too. Has a denominator, and you like fractions, I know, but I'm not really fond of them. Okay? So let's get rid of that denominator. How do we do that? Multiply both sides by the denominator. So that would give us Y times T plus 1 is equal to T. Agreed? Yay or nay? Multiply both sides of the equation by the denominator, wipes it out on the right-hand side, multiplies it on the left. Now what would you do? Does the word distribute ring a bell? What do you think? That would be what? Next step? Ty plus y equal t. Now what do you want to do? Our whole goal here is eliminate the parameter. So you want to isolate the parameter. Which is the parameter? T. So how do you isolate the t? Bring the t over, is that what you said? Okay. By subtracting t from both sides. So that gives you ty minus t. But what else you need to do? Move the y over 2 is equal to minus y. Therefore, I probably would have opted to go subtracting ty from both sides. But it doesn't really matter too much. It's just extra minus signs, and I don't like minus signs. What would be your next thing? What's your goal? Eliminate the t, so you have to isolate the t. So what would you do? What's that?
I would subtract ty from both sides.
Okay, you would have done it the other way. We'll wind up getting it at the same place. Let's use what Dawson wants to do it the hard way, so we'll do it the hard way, okay? What would you do there? Factor out the t. That would be t times. Help me? Second? Y minus 1, is that what you said? Say yes. Okay. Is equal to negative y, right? Now what? Last step. divide by y minus 1. So t is equal to minus y over y minus 1. Okay? Now, I don't like all those minus signs, so what I'm going to do, multiply numerator and denominator by minus 1, and that gives you a y over 1 minus y. Now you only have one minus sign. And that's what you'd have gotten if you had subtracted the ty from both sides. See, if you'd have subtracted ty from both sides, then this would have been y is equal to t minus ty, right? And then factor out the t, and then divide by 1 minus y. So you get the same result, okay? T is equal to y over 1 minus y. Now, the bad news is you got to plug that into your x, okay? So let's do it. X is equal to 1 over the square root of y over 1 minus y plus 1, right? Agreed? Are y'all being agreeable today? Okay. Now what I would do with that is clean that up a little bit and make it 1 over the square root of y over 1 minus y plus 1 minus y. Clean that up some. Over 1 minus y. Because that's 1, isn't it? Okay. So now you got common denominators. So this will be 1 over the square root of, and since you have common denominators, we'll put it all over 1 minus y. Add your numerators. Y minus y is 0, so that would be 1 over that. So this would then be the square root of 1 minus y. Because you invert this, and that's what you get. So, there is an expression. X is equal to the square root of 1 minus y. Now, if we had done it the other way and solved for t in the first equation, here's what we would have gotten. Same thing here, by squaring both sides, you get x squared is equal to 1 minus y. So you could say that would be y is equal to 1 minus x squared. Okay. I like that a little bit better because now it's y is a function of x and you don't have the square root in it. Okay? Now, remember, however, t has to be greater than minus 1. Well, we've lost all meaning for t here. Can I erase some of my scratch here so we can see things a little better? It's all right? Okay. 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 Let's just plug in what's that?
Does that say 1 minus n?
1 minus what?
1 minus n?
I can't hear. Which are you talking
What
about?
does that say? Very far. It says 1 minus, no, above that. What does that say, 1 minus y?
The square root of 1 minus y. Because it's 1 over the square root of 1 over this. So the 1 divided by this, which is 1 times the reciprocal of that. The reciprocal of this is that. Isn't it? Okay. Let me make sure I'm right on it. Ooh. Well. They wound up the same place I did. They got there a different way. They solved it this way. Okay. then they didn't have to mess with the square root later. Okay, but what my point here is we have to account for t always having to be greater than a -1. Okay? Now, if t is greater than a -1, that means, let's just take t equal -1/2. It's greater than -1, so this would be a -1/2 over a +1/2, and that would be, y would be a -1. Okay? And anything greater, like 0, that would be 0. So y is going to be something always greater than on this one, your x's would look like you'd have all real x's, just looking at this part. Okay? Well, wait. Let's be smart about this. This says that y has to also be less than 1. Okay? This right here tells you y has to be less than 1. Okay? Less than or equal to 1. Okay? So y is anything less than or equal to 1. Okay? Now, this tells you if t has to be greater than -1, then let's just again use these are going to be awful, aren't they? This looks like x would be all real numbers, but it really can't. Okay? Can it? For any t large, this is going to be a small number. T of 0 will give you 1. T of -1/2 would be something else. So we probably are going to have some restrictions here, but if y has to be less than 1 for this to make sense, and it does, then that means that the x I guess x could be just about anything, because this value is always going to be less than 1 no matter what your x is. So let's see. Sketch the curve represented by eliminating the parameter, adjusting the domain. Okay, so we've got our function here. So let's write it, let's graph that. I'm going to erase everything and then rewrite the function. Okay? Okay, so y is equal to 1 minus x squared. Okay, now if you were plotting that, okay, you could go up to 1 and normally you would say that, right? That would be the graph of this, because minus x squared would be this one, and you elevate it up by 1. Okay? So that would be that. Now, if t is greater than -1, basically it says y has to be less than or equal to 1, so we see that one. What we can't see right now is limitations on x. This allows x to get infinitely large here's one thing. X is always positive, isn't it? Because this is the principal square root. The numerator is positive, the denominator is positive. So therefore, here is the limitation. You can't have a negative x. So here's what we've got, like that. And we should have been able to recognize that because remember my other rendition of it? When we said that goodness, I'm sorry I erased it now. That x is equal to the square root of 1 minus y. Wasn't that it? Did y'all write it down? Okay. What would that have been? Here would have been your square root function. Only positive. So, now we got them both covered. Okay? X can't be negative, y can't be greater than 1. It has to be less than or equal to 1. So that's what we've got. Because this tells you x's are always positive. This tells you y can't be, well, what we did later tells you y can't be greater than 1. It can be equal to 1, but can't be any greater than 1. Okay. So, that's what we've got. Now, let's see how they did it. They began by solving this one. We started with the other one, which I thought would be nicer too because you didn't have to mess with the square root function. But because it had 2 t's in it, it made it a little messier. Okay? But we wound up at the same place. So what we do here, what would you do first if you're solving that for t? You tell me. What would be your first step? Okay, you certainly could do that, and that would give you x times the square root of t plus 1 is equal to 1. Okay? Next. Square both sides. X squared times t plus 1 is equal to 1. Okay? Next. Second. Multiply the x by what?
Distribute.
Huh? Oh, okay. We're trying to solve for t. Distributing is going to kind of mess up the t. Let's divide x squared. Okay? And then you got t plus 1 is equal to 1 over x squared. Subtract 1 from both sides. So you have t is equal to 1 minus x squared minus 1, which I would then write as 1 over x squared. I said minus x squared over x squared, and that would be x squared, or 1 minus x squared over x squared. Okay? Messy but true. Okay? Then you take that and plug it into the y. Let's see if they got that far as well. I think they did. Let me erase this because you can't see what they did. Okay? They squared both sides to begin with, which is what I would have done, but it works both ways. I wanted you to see it does work both ways. Okay? And then you get t plus 1. They multiply by this and divide it by that. We took 2 steps, they did 1. Okay? And then you subtract 1 from both sides. And then you write that as we did, 1 minus x squared over x squared. That's solved for t. Now they take that and plug it into your y, which is a mess too, okay? Because you got 2 t's in them. So you got a 1 minus x squared over 1 minus x squared over x squared plus 1. Okay. Now that looks worse than what we had before. But what I would do with this is multiply numerator and denominator by x squared. Okay? What that would do would eliminate this one and that one, but make that an x squared. So let's see if that's how they did it. Wow. However they did it, they got the same place we did. This is, in my Cal 3 class, I have an older gentleman in that, and he really hates this book, but I think it's all modern books because they skip steps like crazy. Like, how many steps did they skip to get from here to there? There's nothing intuitively obvious saying that. I said multiply numerator and denominator by x squared, and that will wipe out this and make this an x squared, okay? So that would give you 1 minus x squared over 1 minus x squared plus x squared, which would be 1 minus x squared, because that goes away. So it really wasn't that many steps, but it wasn't completely obvious how you got from here to there. But you see how it happened. So yeah, that is correct. Now, we've written that in, how do they say, eliminated the parameter. So we've done that part, but we haven't adjusted our domain yet. Whoops. Now, we just sort of thought through it before. The rectangular equation, y is equal to 1 minus x squared, is defined for all values of x, but from the parametric equations, which you can't see now, you can see that the curve is defined only when t is greater than or equal to -1. Well, we knew that. Greater than -1, not equal to. We knew that. So then they plotted the parametric equation. Well, what they said to do was sketch the graph using this one. And I said the easier thing would be to sketch the graph using parametric equations. So that's what they did. They started with a small number, -0.75, t is equal to that, and plugged in values and got this kind of stuff, which is not an easy thing either, but that's how it shows that's all you got, okay? Because when you get to -1, you can't go any further. Well, let's see. Well, yeah, t keeps increasing and increasing. If you got to 15, you've still been here. 17, 400 would still be there. You're getting closer and closer to that, but never reach that. Because no matter how big t gets, this is greater than that, so you're approaching 1 and only 1. Okay. Now, that means you only have that leg of the thing. Now, I had the one was okay to have. They say you can't. Because the only way you could get that to be 1 if t was, how do you get that to be 1? It's approaching it but never reaches it. Okay. Oh, over here. Y would never equal 1 because t plus 1 is always going to be greater than t. So it's a fraction. No matter how big you get, 4 million over 4 million plus 1. 4 million and 1. It's awfully close to 1, but it's not quite there. So it never reaches that. So yeah, I'm biased. I didn't indicate that that's a non-reachable value. Rectangular coordinates, you have to do it that way. Usually it's much easier to use parametric equations than to do. The other may help you sometimes, but not necessarily. Now, they're skipping example 3. So let's go back and do example 3. We'll do it right here. And by the way, this one's also at larsoncalculus.com. You can see an interactive version of that type of an example. Okay. Sketch the curve represented by this. X is equal to 3 cosine theta. That's the theta. Y is equal to 4 sine theta. Okay? And given the limitation that 0 is less than or equal to theta is less than or equal to 2 pi. Now, don't even try to solve for theta and plug it in. That's usually the harder way to go. Sometimes when they're really simple, like that very first example we had, yeah, that was really easy to do. This one will not be. So set up your table, okay? Theta is your parameter, and your x is 3 cosine theta, and your y is 4 sine theta. Okay? Set up your t-table with 3 columns in it. And you're choosing 0 to 2 pi. Now, when I'm doing those, I don't like to get a bunch of really complicated things. Let's just do 0, pi halves, pi, 3 halves pi, and 2 pi. You can do some more if you want to, but they just get a little messier, square roots and things like that. This will keep it fairly simple, okay? When theta is equal to 0, what is x? 3. When, what is y? 0. When theta is equal to pi halves, what is your x? 0. What's your y? 4. When theta is equal to pi, what's your x? And what's cosine of pi? Nope. Say again? I can't hear. Cosine of pi. -1. So this will be a -3, and your y would be 0. When it's 3 halves pi, what's your x? 0. What's your y? -4. And when it's 2 pi, it's what? 3 and 0 again. Right? Okay? So you're back where you started. Now, if you do the graph of this, now I was lazy and only chose certain values, but your x's are going 1, 2, 3. I'll put 4, but we're not going to go that far. And this will be, I'll put 5, but we're not going to go that far either. And I should have expanded my graph a little bit. So when theta is equal to 0, you're at 3, 0. When theta is equal to pi halves, you're at 0, 4. When theta is equal to pi, you're at -3, 0, and then you're at 0, -4, and then you're back again, so you're going this way. Now, mine doesn't look like it, but this is an ellipse, and it's going in that direction. And after that, it just starts repeating itself. Thinks it's a Talladega or something. It just keeps going round and round and round the track. Okay? So that's what you've got here. Is that all we're supposed to do? Oh, no! They said sketch the curve represented by that by eliminating the parameter. Are you kidding me? And find the corresponding rectangular equation. I was hoping they didn't say that, but they did. So it really doesn't matter which one they do. They chose the x. So we're trying to eliminate this. This will be x over 3 is equal to cosine theta. And to undo that, you take an inverse cosine. So theta is equal to inverse cosine of x over 3. Goodness, who would want to do it this way? So much easier that way. So your y then would be 4 times the sine of the inverse cosine of x over 3. Goodness gracious. Yuck, yuck, yuck. Okay? You don't want to do it that way. Let's do it the easier way. Let's go on and do the same thing we did there. Y over 4 is equal to sine theta. Okay? Let's not do this at all. Okay? This is awful. Okay? Oops, I just lost part of my parabola. I mean my ellipse. Ooh, that's even worse. Okay. Well, what can we do now? Because we know our trig identity, sine squared theta plus cosine squared theta is equal to 1. Right? So that means we want to square this one. That would be y squared over 4 is equal to sine squared theta, and x squared over 9, I'm sorry, this is over 16. X squared over 9 would be cosine squared theta, right? So instead of sine squared, we put y squared over 16 plus x squared over 9, and that's equal to 1. Now, remember what we did very quickly, but you weren't responsible for them. But in the 10.1, when we had a conic section, remember what an ellipse was? Its basic form, when it's centered at the origin, was x squared over a squared plus y squared over b squared is equal to 1. That's what we've got here, where your a is 3 and your b is 4. Okay? So in other words, your major axis is your y-axis, your minor axis is your x-axis. So that gives you this ellipse. X squared over 3 squared plus y squared over 4 squared is equal to 1. That's an ellipse. Same thing we got here. So much easier to do it parametrically. Why they keep saying change it to eliminate the parameter. Okay? Shoot. Parameters make it easier to plot. Use them. Okay? Now, can I erase this? Okay. Anyone need it longer? Okay. That was example 3, which you can find at larsoncalculus.com. Let's see if they do anything after that. No. Okay. They do have a little bit of a technology thing here using graphic utility in parametric mode, you can do this, and that's what they talk about next. I'll let you look at that if you have it. What we're down to now is page 704, finding parametric equations. Okay? And they jump right into example 4, so let's do it. All right. Find a set of parametric equations. See, before they gave you the parametric equations, they say sketch the graph or come up with the rectangular equation. Okay? Now, they're giving you the rectangular equation and saying come up with the parametric equation. Find a set of parametric equations that represent the graph of this thing using each of the following parameters. Okay? They do the first one nicely. T equal X. Okay? That's the way to go, folks. Find the most complicated part here and let that be T. So if T is equal to X, what's the rest of it? That's your first parametric equation. What's the rest of it? Plug that in here, and what you get? Y is equal to? Pretty easy. I like to write it this way. X equal T. Now Y is equal to? 1 minus T squared. You just got a set of parametric equations. Notice they didn't say find the set, they said a set. Guess what? There's an infinite number of parametric equations you could use. Okay? This is a set, and this is the simplest one. Let X equal T, then Y is equal to 1 minus T squared. So simple. Pick the one that's the most complicated here, let that be your T, and then solve for the other. Okay. Now, this next one, what you want, rather than, they didn't say what it had to be, they chose T for this one because they'd use it in other places. This time they're saying, let the slope M be your parameter, and that'll be dy dx at the point xy. Oh, why would you do that? Okay. Well, obviously, you're going to have to figure out what dy dx is, and what is it? Dy dx is equal to what? Here's your original equation. What's your dy dx? Just 2x. Negative 2x. Okay? And that is your parameter M. Okay? So M is equal to minus 2x. Okay? Okay? Now, what you could do then is like we did before, solve them for x. X is equal to what? Negative m over 2, or negative 1/2 m. Then, y is equal to 1 minus x squared. So what's your x squared? What's x squared? Not that hard. It's what? M squared over 4. So this would be 1 minus m squared over 4. Okay? There are your parametric equations. X equal minus m over 2, and y is equal to 1 minus m squared over 4. Okay? Now, why would you do that? I'm not sure. You know, but that's another set of parametric equations. It's a really round your elbow to get to your ear one, but you can do it. Okay? Now, the y is equal to 1 minus x squared if you graphed it. They didn't tell you to, I don't think. Okay, so let's see what they do from here. We've done what they just said, so let's see how they do it. The first one with x equal t, see that's why I would have said it, not t is equal to x. X equal t, then y is equal to 1 minus t x squared, which is 1 minus t squared. There's your two parametric equations. X equal t, y is equal to 1 minus t squared. Okay, done. Oh, here's Devin. 10 o'clock scholar. Okay. Now, we're only missing Maya and Josh. Haven't seen Josh in an awful long time. Okay. So that's really all you have to do with A. The B part, to write x and y in terms of parameter m, you can proceed, and there's your m is dy dx. You have to go back and calculate what dy dx is, and that's minus 2x, so m is equal to minus 2x. So x would be minus m over 2, just like we did. Then plug that in to your original equation, y is equal to 1 minus x squared. That would be 1 minus m squared over 4. And that's it. All right. Now, so the parametric equations are that. In figure 1024, note the resulting curve has a left to right orientation as determined by increasing the value of the slope m. For part E, it would have the opposite orientation. We didn't do that, but if you use these parametric equations and start somewhere, why not m equals 0? That's a good place to start. Then your x would be 0, which it is, and your y would be 1, which it is. Then go to a larger m, like 2, x would equal minus 1, and then y would equal 0. And sure enough, it is. So you're going in this direction, but if you had chosen m of minus 2, then you would have had a positive 1 and a 0. And that's what you have. So your parabola is doing like that with that orientation. With that set of parametric equations. However, if we were to use the first one, they didn't show it, but let's do it. X equal t, y is equal to 1 minus t squared. Oops, that's not the right way to do it. If this is your 1, let's plug in x equals, or t equals 0, x would be 0, y would be 1. When t is equal to 1, x would be 1, and y would be 0. So this one would be going in this direction. Whereas the m, if you chose that one, is going in this direction. Okay. So you get the same curve, your orientation is just different. Who cares? Okay? That's the curve for the parameter, for the parabola anyway. All right. That was example 4. Moving on to example 5. There's the parametric equations for a cycloid. Now, I've done this many times, and every time you can get really bogged down in details. And we don't have time to get bogged down today. So what I'm going to do is just show you the slideshow, and we'll move right on past it. Okay? Determine the curve traced by a point P on the circumference of a circle of radius A rolling along a straight line in a plane. And this curve is called the cycloid. Okay? So your parameter is going to be your theta, is the measure of the circle's rotation, and we'll let the point P, X, Y begin at the origin, okay? So, when theta is equal to 0, X is equal to 0, Y is equal to 0. So your point P is 0, 0, okay? When theta is equal to pi, P is at the maximum point, and boy, they're just giving you the stuff. Wow. That point will be pi a, comma 2a. Without giving you any reason for that, they're just telling you it is. And it's true, okay? When theta is equal to 2 pi, P is back on the x-axis, but now you're one complete cycle further along, which is 2 pi a. Okay. I wish they had shown the picture first and then done it. Here's where you start. You've got this circle that started down here. This point P was down here at 0. As the circle starts rolling, your theta is increasing, and up here, your basically how far you've gone now is pi a, and that's where they gave you this, and your y value is 2a. It's just twice your, when you're over here, it's exactly twice that. Then you keep rolling, and it comes back down here, but your x is now 2 pi a, and your y is back down to 0. But it's complete rolling. It just repeats this curve and that curve and that curve over and over, and there's your, that's your cycloid. This is what they call a cycloid. Now, what shape are those? I don't know the name for it, except it's the shape of a cycloid. These are not portions of a circle. That's a circle. These are not portions of a circle. Okay? It's just the shape of a cycloid. And they just, out of the blue, give you the parametric equations. A times theta minus sine theta is your x value, and y value is a times 1 minus cosine theta. And that gives it to you. Now, to derive those, it's doable, but it's a really big pain in the neck. And it takes far longer than we have today. So that, for your cultural enlightenment, are the parametric equations of cycloid. Do you think you can get that one in rectangular form? Hang it up. No, you can't. Okay? Possibly polar form, but I'm not even sure of that. Okay? So anyway, yeah, that's the cycloid. Okay? And here is where how they go about explaining this. So this is straight from the book. You can go back and read the book. Let's just keep going here, okay? And this is all good, and it's not that hard to follow once you get the hang of it, but getting the hang of it is a problem. Because the circle rolls along the x-axis, you know that let's just keep going.
We have like 5 minutes.
I know. That's why we don't have time to do this. So there they show it again, and they give the formulas again as if they hadn't already been there. Okay. What I want to get to next is, here is a definition. Between, oh, and they don't even mention it. Oh yeah, here they are. I missed it. The cycloid in this figure has sharp corners here, here, and here, every 2 pi a. Okay? Every 2 pi a, 2 n pi a, you have what they call a cusp. Okay? If you're taking derivatives of this, these would be infinitely negative here, infinitely positive here. Discontinuity in the first derivatives, okay? But in between that, they're called smooth. At the cusp, your first derivative goes haywire, okay? But in between, you've got smooth curves, and that's what they talk about here. Here's a definition of a smooth curve. A curve C represented by some y is equal f of t, x equal f of t, and y is equal g of t on some interval I is called smooth when f prime and g prime are continuous on that interval I. Not simultaneously zero, okay? One could be a zero, but the other can't, okay? Except possibly at the endpoints of the I where you could have cusp. The curve C is called piecewise smooth when it is smooth at each subinterval of some partition of I. Sort of like we just saw with the cycloid, okay? Again, we don't have time to do all that, so you're not responsible for this one. These are related to cycloids. The tautichrome and the brachistochrome, okay, problems. And if you'll see there's James Bernoulli, who looked like just such a genial old fellow, doesn't he? He was a real pain in the neck, I understand. When his son beat him out of a contest, he didn't even know his son was in there, and he kicked the son out of the house. He said, okay, you're on your own. So he's not a very pleasant guy. And that, he had a brother too. They fought like cats and dogs too. James and let's see, was the older brother of John. Okay, and then they had kids. Daniel Bernoulli was one of their sons. The whole family of brilliant mathematicians, but not the nicest people in the world. Okay. The cycloid is related to one of the most famous pairs of problems in the history of calculus. The first problem is the tautichrome problem. Began with Galileo's discovery that the time required for a complete full swing of a pendulum is approximately the same whether it makes a large movement at high speed or a small movement at a lower speed. And this is what you had there. The time required for a complete full swing of the pendulum starting from point C is only approximately the same as the time as it started from A or B or wherever, it just goes back and forth. This is the principle of a grandfather clock. Okay? If you have it set up properly so it makes one cycle in a second, that's your timer for a second. So that your grandfather clock or grandmother clock either keeps good time. Galileo realized that he could use this principle to construct a clock, which he did, and he was the first inventor of a workable clock. However, he was not able to conquer the mechanics of the actual construction. Okay? He was a great physicist, but probably not the best technician. Okay? So Christian Huygens was the first to design and construct a working model of this, and they don't give the timetable on this one, but it came up quite a bit later. He realized that the pendulum does not take exactly the same time to complete swings of varying lengths. But in studying the problem, Huygens discovered that a ball rolling back and forth on the inverted cycloid. Remember the cycloid was like this? Flip it over, roll the ball back and forth, then you see it's exactly the same time. Whereas a pendulum is a portion of a circle, and that's why I said a cycloid is not an arc of a circle. It's slightly different. But if you have a cycloid, that does make exactly the same. Okay? The second problem, which was posed by John Bernoulli, our friendly character there, in 1696, is called the brachistochrome problem. In Greek, brachis means short, and chronos means time, short time. The problem was to determine the path down which a particle will slide from point A to point B in the shortest time. If you have an inverted cycloid again, the solution is not a straight line from A to B, if you just do like this, that's not your shortest time. Actually, if you invert the cycloid and do that, and you will get the shortest time. Because you see, down a straight line, your initial acceleration is less because your angle is greater. So this acceleration is pretty great, so that gets it rolling faster, and even though it has further to roll, it gets there in the shorter time. And again, the inverted cyclone does that. Cycloid. So I wanted to at least expose you to those two greatest problems in calculus ever. Okay. The amazing part of the solution of the brachistochrome problem is that the particle starting at rest at any point C, not just A, C, here, wherever, is that the particles starting at rest from any point C between A and B take exactly the same time to reach B. So if you started here and if you had two identical ones, started one here and one here, you would think this one has a head start, right? No. They would get there at the same time, exactly the same time. Because you see, you miss that rapid acceleration you have here, and you're starting from here, and in time, the same time, they'll wind up at the same point. Pretty incredible. Okay? That's it for 10.2. Do we have time? No, we don't, do we? For 10.3. Sorry about that. Yeah. Okay. That makes your final exam, the last test, awfully easy and awfully short too. Sorry about that. So it's not going to take you all that long to do it. If I can find it in here. Here we go. Okay. That's not it. That's test 2. Here's test 3. Okay. Now, before you leave, there's one correction on here. I forgot to put the set of parametric equations, and I need to do that for you before you go. Is it ready to me? Good deal, thank you. Oh, fantastic. Excellent. Okay, that one's good. All right. I want to put the, oh, did I end? Yeah, I did. Good. I was scared. Okay. Let's go back to this last slide here, and let me, your problem 5, I forgot to put the parametric equations. So, test 3, oh, who cares? That was 10.3. We didn't get to 10.3. So basically your test is the first 3 questions. Question 1 is from 9.1. Question 2 is from 9.2. And question 3 is from 10.2 that we just did. So questions 4 and 5 are totally optional. If you want to do 10.3, here's your nice even plot. Yes.
Will we get like bonus points if we do?
Yes, that's what I was just going to say.
If we get it wrong, does that take away though?
You just lose. You fail the course if you get them wrong. No, I'm just kidding. Okay. No. So let me go on and give you the test 3, question 5. Okay. Your parametric equations are x is equal to t plus 2 and y is equal to t squared plus 6t. I was making copies when I realized, I left off the equations. Okay. So here's what we got. Question 1 is from 9.1. Question 2 is from 9.2. Question 3 is from 10-2, and questions 4 and 5 are from 10-3, which we didn't get to today. So if you do 4 and 5, if you get them, you got to get them exactly right. If you do, you get bonus points. If you get them wrong, you don't lose them. Nothing is wrong. If you leave them blank, nothing is taken off. I'll just grade on 1, 2, and 3, and then 4 and 5. If you get them perfectly correct, you get bonus points for those. Okay? Sorry, it's so easy and so short. Get over it. Okay. All right. Now, for those who came in a little later, let me repeat some things I said earlier. Number 1, they did complete, finally, open student course evaluations. So please do your student course evaluations. Please do those. Okay? Number 2, I'm just giving you the test. Listen to the first part of the today's YouTube video, and I go over in gory detail where I'm going to be, when I'm going to be there for the next 2 weeks. Okay? So, any questions? Been great having you in class. Get these back to me anytime. If you finish them by tomorrow, bring them tomorrow, or later today, I'll take them. But for those, if you are looking for me on the Birmingham campus on Friday, I've got a doctor's appointment Friday, so I'll only be there from 8 until 8:40 Friday on the Birmingham campus this week. Then I've got the doctor's appointment. If I get through in time, I'll go back. But I don't think I'll get back there before 11 anyway. But if things go long at the appointment, I may not get back there at all. So that may be the only time I'm there. But then next week, on this campus most of the time, Wednesday afternoon on the Birmingham East campus, and Friday on the Birmingham West campus. Are any of you graduating this term? You two are, okay? Be sure you get me your test. Try to get them as soon as you can. All your tests, your research paper test, everything, because I don't think they set an earlier time for your grades to be in. They do in the spring, but they didn't for this fall. So try to get them to me as soon as possible so your grades will be in. Everybody else, your grades don't need to be in until Monday noon. But for those graduating, get them to me as soon as you can. Okay? It's not going to bother your graduation. Okay? They're not going to refuse to have you graduate. Okay? So, everybody got that? Been great having you in class. Congratulations on the graduates. And get me your work as soon as you possibly can. I'll be here. Any questions, come see me. I'll be glad to try to answer them. Yeah.
So if we're doing the shell method, and I have, and it's on the interval from like 0 to 3, and it's about the line of x equals 3. Would
Rotating around that?
Yeah. Would the p of x be 3 minus x, or just x, since it's already the distance between the y-axis and x is at 3?
Okay, this is your radius function. Is that what that is?
Yeah, the p of x.
P of x, okay, and that's the radius function if I remember right. Okay, since you're going around here, it's 3 minus x would be your radius.
Okay.
That's what you're asking. Yeah. Yes, sir.
I'll be on UAB tomorrow.
Okay.
Can I email you the test?
Sure.
Okay.
Okay. But you can do it anytime next week too. But if that's easier, you can email it to me. That's fine.
Okay, anytime next week.
Okay. Do you know if there's any time particularly you need the transcript to go back? Just before the first of the next
I
term?
would say before
January, something or other. What I was going to say, I'm not in charge of doing transcripts. So check at the registrar's office and see how you get that done. There's a form or something you could do. You probably can go online and do it too, to check with them and see if you need that. Sit back as soon as possible, and as soon as I get the grades in, they'll try to do that.
Okay, thank you.
See, I don't do that. They do it. So that's why I was trying to get you.
Okay, so about research paper, I tried to print the,
Thank you.
you know how you wanted us to print the cited pages, you kind of printed it kind of weirdly, is that okay?
Yeah, that's fine.
I just wanted to make sure.
That's your, yeah, source. Yeah,
source.
Perfect.
You want me to just have it behind there, is that fine?
Um,
Not stapled or?
here's what I think I would do, just so it doesn't get lost. I'll just do that.